Hello, everyone. Welcome to our presentation. My name is Lucas.
I'm Jonas.
And welcome to KernelSnitch. Leaking kernel heap pointers by exploiting software-induced side-channel leakage of kernel hash tables.
What a title.
Yes. So what is this presentation about? This presentation is about KernelSnitch, a novel operating system side channel. KernelSnitch exploits the timing that accesses of hash tables have different timing accesses. In this presentation, we also present information leakage amplification to make this timing difference exploitable from user space as unprivileged and untrusted users. Also, we present a kernel heap pointer leak in under 1 minute. Crucially, this is the first kernel heap pointer leak using a side channel. And lastly, we will show a live presentation where we leak the struct on this laptop, where we currently play the presentation. Again, I'm Lucas Ma. I'm a PhD candidate at Graz University of Technology. My research area is system security, especially kernel and side channel security.
Hi, and I'm Jonas. I'm also a PhD candidate at the Graz University of Technology. And my research fields are also side channel security, but also a bit more low-level microarchitectural attacks and rowhammer. And I'm done pretty soon, so I'm looking for a job. Okay, let's jump right into it with the motivation and some background that you will need. So all the computers you're currently using consist of hardware and software, as you obviously know. And this hardware consists of CPUs like DRAM, disks, and stuff like that. And the problem here is that all of those devices are susceptible to side channels. It can be cache and timing side channels in the CPU, also timing side channels in the DRAM. You also have like EM radiation on the CPU. On the disk, you can have timing side channels, contention, sound of HDDs, and stuff like that. And on the application side, it sadly looks the same. We have side channels, for example, in encryption algorithms, cache side channels, timing side channels, as well as in compression algorithms, and nowadays also in neural networks, side channels are everywhere. But just for a second, let's imagine a perfect world where we can solve all the side channel leakage in your hardware, all the side channel leakage in the user applications you're running. Would this solve this problem? Sadly, it won't, because there's still the operating system in between. And the problem here is that the research on operating system side channels is pretty sparse. And we are one of the first ones that go into this a bit deeper. Okay, let's do a short background on linked lists, because they're the basic building block of our side channel. I think probably most of you implemented some linked lists in some programming beginners course some time back. Just a short reminder, so it's a simple data structure that holds elements of the same type. And if it's empty, accessing a linked list obviously is pretty fast. There are no elements in it. But the thing is, to go through a linked list, one has to iterate over all objects. So if there are more elements in a linked list, it takes longer and longer to iterate over the linked list. And this is also a problem, because if we have a linked list and it has a lot of elements, it's slow to go through the linked list. And we want our kernel to be fast, obviously. So what the Linux kernel implements a lot and uses a lot are so-called hash tables, where we don't use a single linked list, but split this one linked list up over multiple linked lists. So we now have multiple linked lists. We call them buckets. And when we want to add an object to the linked list, we have some hash function that's pseudo-random and basically selects one of the random buckets to put the object in using a key that then computes the bucket index.
All right, okay, so now we know about linked lists. We now know how the Linux kernel implement hash tables. I would say let's combine both. And if we combine both, we get exactly KernelSnitch. KernelSnitch, so from a high-level perspective, we have the user space on the top and the kernel space at the bottom. In the user space, let's say we have two processes running, one which is under the control of malicious actors, and one maybe also under control or controlled by someone else. And inside the kernel space, there are a hash table, which is only accessible if your code currently runs in kernel space. And what we now do, the process one, so the process controlled by us or by malicious actors, calls a syscall, where the syscall accesses the hash table. In our case, it accesses the hash bucket. The hash bucket one, is on this high level slide empty, so the access will be notably fast because no additional elements has to be accessed from the bucket. And then we let process 1 idle till another process, maybe under our control or controlled by someone else, calls a syscall, which modifies exactly that hash table. In our case, it appends 5 elements to the hash bucket 1 of the hash table. And let's say after some time again, process 1, so the process controlled by us, we call the same syscall, which re-accesses the hash table. Now the hash table has 5 elements instead of 0. The access will be notably faster compared to the first syscall. And what KernelSnitch does, it deduces security critical information from this timing difference. But before we go into detail of which security critical information, we need some kind of primitives. The first primitive is an access primitive, and the second primitive is an append and remove primitive. Access primitives are very simple, are syscalls, which internally accesses structures, in our case hash tables, and there are a lot of such access primitives, but let's consider this very simple one. Later we will show a more complex for the actual attack, but in the beginning let's consider getting the time from a POSIX timer. The syscall for it is clock get time. It takes one argument, the identifier of the timer, where in the first stage the syscall takes this argument, so this ID, and one kernel address, the kernel address of the signal struct, and calculates a hash using the timer hash function. This hash is the index where we obtain a reference of the hash bucket. And then in the last step, we iterate over all elements of the hash bucket, and if we provide an ID which does not match any of these elements in the linked list, in a bucket, then we leak the entire occupancy level of this hash bucket through the timing.
Yeah. And then we also have an append and remove primitive. These are syscalls that modify these data structures inside the kernel. And for example here, also for the POSIX timer, we have this timer create syscall that basically does the same thing again. It first calculates a hash, then it selects the correct bucket based on this hash, and then it adds a timer to the linked list. So with this syscall, we can make the list longer. And then from the user space side, the code also looks pretty simple. What we do here for one of our first measurements, we just used invalid IDs. As Lucas just said, we need invalid IDs because then the syscall iterates over the whole linked list, so we actually get a timing leakage. And then we simply take the time of the syscall. So we take a timestamp before and after the syscall was executed, and this leaks the occupancy level. And so we did this on a real system. We performed 1,500 times 512 accesses to this bucket. Of these 512 accesses each, we took the 8 fastest and then the average of those. This removes a lot of noise from the system. And the buckets are either empty or have a single timer in them. And if you look at this graph, we can see that we see a beautiful timing difference between an empty bucket and a bucket with a timer in it. At like 165 timestamps, we see that we can easily distinguish these two levels. Isn't this a nice graph, Lucas?
Oh, but wait, no, it's not that nice, because if you maybe see on the left and on the right, there's some kind of problems. These are false positives and false negatives, which will reduce the accuracy of our side channel, and for later the kernel heap pointer leak, these are not acceptable. So we know we have the side channel, but we need to make it more precise, better, with less false negatives and less false positives. What we did there, we did some timing leakage analysis for that. Again, we analyzed the code in more detail. So we analyzed the struct, which is stored in the hash bucket. It consists of one ID and the signal, as I said. The function which iterates over the element is POSIX timer find, and it does basically that. So all timers within the bucket, if the signal is the same as the argument, similar to the ID, it returns the timer. And what we now aims for is to make this timing difference exploitable from user space. And there are two possibilities how to make this timing difference larger. The first one is to make the list bigger. And the second one is to make these accesses slower. Now let's consider these two cases into more detail. Make the list bigger, so it's pretty straightforward. If the hash bucket has 0 elements compared to 1 element, the timing difference is notable, but not that large. However, if it's before has 0 elements and then 5 elements, the timing difference will be significant, or will be at least higher compared to 1 element.
I guess this doesn't come to a big surprise to anyone here. But we are also microarchitectural security researchers, so of course we have to use the microarchitecture at least a bit. And we also consider CPU caches, because here, when we iterate through this linked list, we access all these objects that are spread out over the memory. And on the first access, or the first call of the syscall, they're probably uncached, but then they will be cached, and so iterating over this linked list is pretty fast, because they're cached. If we now are able to enforce a cache miss on every iteration over the linked list, we will see a large discrepancy in the timing. And this is what we basically do. Before calling the syscall, every time we flush the CPU caches by simply accessing a big array. Accessing a big array is definitely not the best way to evict CPU caches, but we don't really care about performance here. And accessing a big array is really nice because it works on pretty much every CPU. We don't need knowledge about CPU replacement policies or anything like that. Big array, and it works on x86 ARM RISC-V. Yeah. And so we implemented these two things. We implemented the cache flushing and also tried different bucket sizes. We ran the experiment again. Now 4000 times 512 accesses. Again, we take the average of the 8 fastest of each measurement. And now we measure the difference between 0 and 5 timers. And this is now really nice. So if we compare to the previous graph that you saw, already 0 and 1 timer are now easily distinguishable. They don't stick together at all. This is because of the cache flushing. And if you look at 0 and 5 timers, for example, the difference is huge. And we have basically no false negative, no false positive in this measurement. So this works now really reliable. Okay, this was the first part of our presentation, the basic side channel. Let's reiterate what we saw. So we have these access primitive syscalls that leak the occupancy level of hash buckets through the timing. And then we have some append and remove primitives that allow us to modify these kernel structures, the hash buckets from user space. And we are able to amplify the leakage wide enough so that we can actually measure this from user space pretty much perfectly without any false positives or false negatives. Nice.
Okay, then let's continue. What can we do with the side channel? As I said in the beginning, we perform a kernel heap pointer leak. So we leak the location of heap objects in kernel space. But before going into detail of the attack, let's provide some motivation why this pointer leaking is a significant thing. So let's consider traditional kernel exploitation. For traditional kernel exploitation, we assume that a malicious actor has some kind of code execution as an untrusted and unprivileged user. And what the malicious actor first do, it triggers a vulnerability. In a lot of cases, it's a memory corruption vulnerability, where the first step by triggering the vulnerability is to get some kind of read primitive. This read primitive then returns code addresses and heap addresses to the exploit. In the second step, the malicious actor triggers either the same vulnerability or another vulnerability, depending on which capability the vulnerability gives you, to obtain a write primitive. This write primitive is then used for one of two attacks, in most of the cases, a control flow hijacking attack or a data-oriented attack. I won't go into detail, but the goal of both is to perform privilege escalation so that before the attack, the malicious actor is unprivileged, and afterwards it's privileged to fully compromise the system. The problem with traditional kernel exploitation is that by exploiting vulnerabilities, we put the system in a state which is undefined. And this undefined state may cause system crashes, and the system crash for kernel exploitation mostly results in reboots, which is not acceptable for if you want stable and reliable kernel exploitation. So what we do with our leak, we exchange this read primitive with this kernel heap pointer leak. But crucially, we use the syscall interface as intended. We don't put the system in a state, or in the first stage of the exploit, in a state which is undefined. So we bypass the first part where the exploit may cause some system crashes. So overall, with side-channel supported kernel exploitation, we increase the reliability and the stability of kernel exploits.
Okay, so.
Let's recap the access primitive again. So the access primitive takes one kernel address and one user identifier from the syscall arguments, and it calculates a hash to obtain the index of a hash for indexing the hash table. And when we analyze this line into detail, we know the hash function because the Linux kernel is open source. We can watch it up. And we know the user identifier because we call the access primitive syscall with whatever we like. So we know these two things. But what we do not know is the kernel address. And that's what we aim to leak with our kernel heap pointer leak. Therefore, we perform our exploitation strategy in an online phase. Works as follows. We call the access primitive with different user identifiers, where these different user identifiers still uses the same kernel address. And inherent to the principle of the hash table, different user identifiers and the same kernel address will result in obtaining the same index for the hash indexing. So they will result in hash collisions. And we then use our side channel to detect exactly these hash collisions, or when these hash collisions occur. Simply, you can see it as we obtain a unique fingerprint when using different identifiers. And in the next step, in a brute force offline phase, we test all possible kernel addresses to match exactly that fingerprint we previously obtained in the online phase. So we match exactly these hash collisions.
Okay, let's look at the attack scenario. The data structure that we target now is the futex hash table. It's used to store data for fast user space mutexes called futexes on Linux. The user ID that we supply is a user address, so address of the user space virtual memory. And the kernel address that we will leak is the address of the MM struct. The MM struct stores pretty much all important data about the virtual memory of a process. So it has quite interesting stuff in there. We target x86 64-bit for this exploit now because this is a machine for x86 64-bit. But the same thing works on ARM and RISC-V on every other CPU as well, because all the leakage happens only in software, and except for the caches, we don't lease any hardware for our side channel. And then the leak takes less than a minute, as you will see soon. Let's go for the access primitives again shortly, because they're pretty similar to the POSIX timer primitives we saw. So again, we compute the hash table, we compute the hash, and then index the hash table with it, iterating through a bucket of this hash table. And then we have the append and remove primitive, futex wait, which is a bit more complex here, because you actually have to put a thread to sleep with this syscall. So you cannot simply create timers, you have to create threads, put them to sleep. So the user space side is a bit more complex, but in general, it's exactly the same. And then for the online phase, we do the following.
Exactly. So as I said previously, we now try to detect a hash collision for different IDs. In our case, we want to define 15 IDs that cause a hash collision. For that, we first need a large array. This large array stores the user identifiers or user addresses for the access primitive or for the access and append remove primitive. Second, we need an array which stores all the identifiers we then use in our offline phase for matching the fingerprint. And what we did as an initial stage, we obtained the access timing of an empty hash bucket. So we did it by first flushing the CPU cache, so iterating over a large array. Then we get the timing of the futex wake with an invalid address. And that timing difference, so that syscall timing times 10 is now our threshold. So if a timing is 10 times larger than an empty bucket, we know there are a lot of elements inside the hash bucket. A lot in our case means 4069 because we now append to one hash bucket 4069 vertexes. So now we have two timings, so so that's basically what we did with what's the
I mean, we have an empty timing and this timing with like 4,000 entries.
Exactly.
Big difference.
And in the next stage, we find the collisions where first we again flush the CPU caches and get the timing of the syscall. And as I said previously, if the timing of this exact syscall is larger than a threshold, so significantly larger than accessing an empty hash bucket, we know we found one collision. We found the collision where we, in the second step, appended the 4069 vertexes.
Great. So we now have this fingerprint, which are 15 addresses, user addresses, which are the user IDs, that are in the same bucket where these 4,000 elements already were. And now all we have to do is try all the possible kernel addresses and see. We couldn't do this because we know the hash function. We do this not with kernel interfaces, but actually implemented the kernel hash function ourselves. So we write a small program that just goes over all the addresses and measures the collisions. And here we try the first address. There are no collisions there. We try the next one. We find like 2 of the 15 colliding. And we do this just for all addresses. And after some point, we find this one kernel address where exactly this hash function that we know produces the hash collision. And this happens only once, and we know the kernel address of the struct. That's basically the whole thing. The problem here is we have to try a lot of kernel addresses, and if we would try all of the kernel addresses there are, this would not finish in under a minute. This would be pretty unpractical, but there are a few nice things in the Linux kernel that help us reduce this search space by a lot. So if we would just go through every address in the kernel, we would have to search for 2 to the power of 46 addresses, which is way too much. That's not possible. But let's look at a few things. So heap pointers are always in a direct physical map. That's gigabyte page aligned, so it doesn't influence our next steps, which is quite nice. And now looking at the direct physical map, structs are always inside struct slab. And on this machine, for example, this struct slab is 8 pages large. So this reduces our search space by 2 to the power of 3, which is 8, and 2 to the power of 12, because that's the size of a page. And then inside one struct slab, we have 23 locations where the struct could be, because they're in the slab just behind each other, like this. And there are 23 possible locations in one slab, and this reduces our search space from 2 to the power of 46 to 2 to the power of 35.3. And this is pretty doable on this machine.
So what we need, as Jonas said, we need to know how large the struct slab is, and we need to know how many objects, so how many structs are within one slab. This depends on the system. That's a typical thing for kernel exploitation. So most kernel exploits need some kind of information of the target system. Our target system is the Ubuntu Linux kernel 6.8.0 minus 52 generic. That one was at least last week the most recent Linux kernel, Ubuntu Linux kernel version. And we need, as I said, two things, the slab page order size and the struct size, how many structs are within one slab page. And we did it pretty straightforward, so that there's a directory in a Linux kernel, syscalls slab struct. We grab all files, and 3 files are important for us. The objects per slab, so 23, as Jonas said, and the page order. So the slab page order is 3, 8 pages, as I said, yeah, it's similar to Jonas, and the size of the struct, which is 1,408.
But Lucas, you're using roots to get these numbers, right? That's not a good exploit.
Yes, that would be a terrible exploit. But well, one important thing is these values stay consistent for the system. So if I know Jonas uses the same system, I just use them because they're the same.
And you would, if you want to weaponize this exploit, you could just have a big lookup table with kernel versions and
exactly.
This constant.
So that's a very typical thing for kernel exploits. Yeah. Okay, then let's say let's leak some kernel addresses. As I said, we have a live demo here.
I think you can look down there.
Oh, perfect. Okay, it consists of the, So our exploit or our demonstration consists of one file, the struct leak file, and one kernel module. We use the kernel module to obtain the ground truth, so to obtain where the struct really is. And we use,
We use this module just at the end to check if our leak was correct.
Exactly. And then, now let's start it. First, we find the collisions. So the collisions were found in like 1 second, and that's the brute force phase. On this system, I start 16 threads, which now tries all these possible kernel addresses for the struct. And yeah.
It should be done any second now.
Hopefully. Yes, it tries different addresses, and at some point, it should print out the correct address. And we see it's a success, so we get exactly that address, and the kernel module verified it that it's the same. And the time, it took about 30 seconds, which is pretty fast. What we did then, as security researchers, we disclosed KernelSnitch to the Linux security team. And how did they respond?
So Linux was like, KSLR is broken for local access anyways. There's like no way to actually protect the kernel against KSLR leaks, so there will be no mitigation.
Shortly after, Keyscook responded, no. We leak heap KSLR, not code KSLR. Heap KSLR is hard to expose, even locally. So Keyscook presented a patch. Let's go through this patch. So that the vulnerable indexing for our case, for the Vutex case, is just calling the hash function. And the patched version is, again, calling the hash. Using this key for subsequent computation, it XORs the swapped bytes, so it swaps the most significant bytes with the least significant bytes of the Vutex hash table and XORs it to the key. And next, it XORs the key to the code base address and returns this key.
So it basically just adds a bit more randomness so that the brute forcing phase would take longer, right?
Yeah.
Which is reasonable to do. Linus Torvalds thought differently. He was like, what voodoo programming is this? And rejected the patch.
Yes.
And this basically means that this is still exploitable to this day, and currently it does not look like this will be fixed in the upstream kernel. And with this bad news, let's jump to the summary and some takeaways. So we present the KernelSnitch, a timing side channel on hash tables that's software-induced and only coming from software. We can amplify this leakage to make it usable from user space and have like perfect measurements, basically, from untrusted and isolated users. And we showed that we can actually exploit this side channel to leak heap pointers, which are important for kernel exploitation in less than a minute. Yeah.
So the takeaways of this talk is with KernelSnitch, we open up a mostly unexplored field of research of side channel side channel attacks, exploiting the side channel leakage of the operating system. Crucially, KernelSnitch is not an end-to-end privilege escalation exploit, so it not allows you to obtain root. However, it leaks addresses which are relevant for kernel exploits. And with these addresses, and given a write primitive, so we still need some kind of write primitive from a memory corruption vulnerability or any other kind of vulnerability. This makes kernel exploitation notably more reliable and stable. And with that, we are finished with the talk. If you have any questions, please come forward to the microphones. And thanks for your attention.